I don't want to grow up, I'm a curious kid. The world has 100 questions I can...
Good evening and welcome to Oumuamua, Interstellar Visitor. I'm Tucker Hyatt, founding director of Wonderfest, the Bay Area Beacon of Science. And I'm honored to represent Tinka Ross, who's in our audience tonight, illustrious founder of the Mount Tamalpais Astronomy Program. Our speaker this evening is Douglas Lin, Professor Emeritus of Astronomy and Astrophysics at the University of California, Santa Cruz. Go Slugs. Dr. Lin is also Director Emeritus of the Kavli Institute for Astronomy and Astrophysics at Peking University. Doug earned his BS, his Bachelor of Science degree at McGill University in Montreal. He then went, as they say, across the pond to Cambridge to earn his PhD. Finally, Dr. Lin did postdoctoral research at Harvard before making his academic home at UC Santa Cruz and Lick Observatory. Doug has earned many fellowships and honors in his astronomical life, including Guggenheim, von Humboldt, and Royal Astronomical Society fellowships. Doug was elected to the American Academy of Arts and Sciences, a great honor. And in 2015, he was awarded the highest honor of the Astronomical Society of the Pacific, the Bruce Medal. Please welcome the highly decorated and often decorous Dr. Douglas Lin.
Thank you very much. I'm going to talk today about this very strange object, interstellar visitor called Oumuamua. And, usually when it's a strange visitor, and you often wonder, why are you here? And the reason, let me see if I can take over. Yes. The reason that we wondered about this question is that it affects our immediate neighborhood, and as it has been in the past. And I think since we're a young child inspired by, among many things, dinosaurs, we realized that the Earth may have been visited by extraterrestrial rock, which made a giant impact and killed off dinosaurs 65 million years ago. And these rocks come from asteroid belt region. And in the solar system, there's plenty of asteroids. In the last few years, we're starting to discover many, many more. And here is their distribution on a sort of grand scale. Some of these asteroids appears to actually cross the orbit of Earth. So if you sit on the orbit of Earth and you see some of these asteroids come and go, some of them fall in to make these meteorites, and but hopefully we can avoid some big ones, like the ones that killed off the dinosaurs. And it would be very important for us to try to trace their motions, and we see them with various monitor instruments and try to look at their orbits and provide some guidance on how to develop a strategy to avoid catastrophe. One of these surveys was done, it was pioneered on Haleakala, on the summit of Haleakala in Maui, and that telescope, a 1.8 meter telescope, was commissioned to search through the sky. And this telescope is very carefully designed to get very sharp images, so you can actually see over a large degree of field, and you can look at the sky throughout the night, and night after night. And it's a survey telescope, and it can generate something like 10 terabyte of data a night, and it has enormous, giant football field of pixels, it can pick up all of these images. So what it does is that sometimes it looks over the same region of the sky, and it looks over and over again in this region. When you look over and over again, from time to time, you can see that the position of the stars may move across the field. And that is normal because the Earth itself is rotating. So if you take an image every for 1 minute and every 15 minutes, you can see these dots move around. And all of the stars seems to be moving, but every now and then you see 1 or 2 stars which do not follow the rest of the pack. For example, here is something that is right down, it's not moving at all, and some may even move sideways. And this way you can actually survey, here's the sun, you can look in the direction away from the sun at night, you can look through the entire sky, and you can gradually pick up information. And what are you looking for? So if we now make sure that we correct for the rotation of the Earth, and we can sometimes see here, there's the galaxies and stars, they're at the same place. But every now and then we see one of these objects that appears to be here at one particular time. On the next frame, 15 minutes later, is moved over here. And that positional change represents a motion of this object in the sky, then moved from here to here, and you wait for another 15 minutes, it will be here. So this way is called, this method is called astrometry. From using this method, we can determine the speed of all these objects as they go across the sky. On October 25th, 2017, a particular object was found that was peculiar, that stand out from everything else. And with this method, actually, we find thousands of tens of thousands new objects, but this particular object really stood out. It's called A2017U1. And very quickly, it was realized that this object has a speed that is moving so fast, and that it corresponds to an orbit with an eccentricity of 1.2. What that means is that this object is coming into the solar system and going out of the solar system at the same time. It's coming in for the first time, and it's going out on its way out. And when we saw it. Now, if you look at all of the other asteroids, you look at their closest approach to the sun versus their eccentricity, you find all of the asteroids are on eccentric orbits, and there may be a few on nearly parabolic orbits, but most of them are on eccentric orbits. But this one really stood out. And this could not be an observational error. And we actually observed several times and throughout the night to get this information. So if this thing is on the way out, it's coming in for the first time. And since that we only turned on this telescope in the last few months since its operation, and you can then infer what is the probability of us seeing an object that is coming and then leaving. It is like when you are waiting in the field and all of a sudden you see a deer crossing your horizon, but is running away very quickly, and then you wait for another hour, and for example, and you may see another one, so you know how many deers are there near this region. Here we haven't seen the second one as far as objects similar to Oumuamua, and so we're seeing it only one event. But it was an event that we detected within a few months after the telescope was switched on. And so this event must have occurred very frequently. So to work it out, how many of these objects are in the nearby region if they were to come in and out like this. And we think there could be as much as tens of Earth's mass of these objects, and maybe something like a trillion or quadrillion objects per parsec out there. So the detection of this object immediately raised a lot of interest, and people were following up all of the telescope around the world, and they were tuning in, try to follow, to get a glimpse at it, because the object is moving away, it's going away very fast. So everybody wanted to have an opportunity to see it. And here's an example within the 1 week, and already there are several different telescopes has tuned to that direction and try to observe what is going through. And what they see is that the brightness of this particular object was varying in time, and it's going up and down like this, changes by almost a factor of tens to almost 100. So this kind of variation is probably due to the reflection of the light onto an object which has got an odd shape. When you have an odd shape like this, there's part of the light that will come in that's facing the sun. There are other parts that's dark, and if it's elongated, and then you can see the light variation as it moves around. But this kind of variation could be represented by say a French bread baguette type of object, and that is going up and down, tumbling, and like this rod that is falling and tumbling in this manner. Or alternatively, it could be something that looks like a frisbee. And I'm not a very good frisbee thrower, so when I throw my frisbee, it tumbles all over the place. And if you have a light that shines on it, and you can have this kind of variation. So we know this is a common phenomena amongst the asteroids. We look at many asteroids, we can determine their shape, and it's best to describe it in an idealized way, not quite like a ball, but something more like a football, and with 3 different axes, the longest axis, and being A, and then the shortest, shorter, and still shorter. So if there are, in this kind of configuration, they may have 3 axis ratio, and if they look something like a hamburger, and they would be classified in this region. If they look more like a hot dog, they would be in this region. So the light curve of Oumuamua can be characterized either as a hot dog or as a hamburger. It's probably a little bit more likely to be a hamburger than a hot dog, but we can't distinguish it. In any event, the shape, if it is a hot dog, the shape is almost 7 or 8 to 1, and in terms of elongation relative to the radius here. And if it's hamburger, it's almost like 6 times in width compared to depth. In addition, this object is tumbling with some sort of a frequency. It's rotating, and but it's not a regular rotation. It actually is more like the frisbee example I gave you, and it's tumbling all over the place. And this again is not something that new, because we see in many asteroids, they go through this type of tumbling that depends on their diameter and depends on their, so we can detect these asteroids, and they are spinning and tumbling at speeds that give you a period of order 8 or 9 hours. There are many of them. So this is the regime that we see of Oumuamua. So the other thing is, because there are so many telescopes were available to look at this, So we can actually look at the color of this object and see whether it has certain type of color. The color is mostly reflected light, and some of it is absorbed, re-emitted light. And because it's reprocessing the solar radiation, we can tell something about their composition. And it seems that Oumuamua is more like a rocky object like Earth or Mars or some of these rocky asteroids, rather than comets, which is more icy and it has a more reddish color and with a different albedo, albedo being the reflectivity. And the plot thickens when we try to detect, try to measure how much carbon dioxide, carbon monoxide, and other things, and try to look at the composition. And what you find is from the spectra of Oumuamua, and that it's more like Earth type of objects than like chondrules and comets. So, and the final puzzle came in is when people follow this for several months, and when it's fading very fast, and they can plot its position in the sky and look at how it's moving around and is following certain paths and it's going away. Now, we all know that more than 300 years ago or 400 years ago, when people like Halley, and when they look at comets and they can figure out, you know, the orbit, and by constructing an orbit which is used by Newton to determine the law of gravity. So from that law of gravity, then Newton was able to predict where Halley's comet would be. And you can use the same method here and try to do the same prediction for Oumuamua. And what you tend to find is that when you make that prediction and then try to observe it, and there's a little offset in the position that from prediction versus actual observation. So people refer to this as a non-gravitational acceleration. And that's very odd. So to summarize the odd characteristics of our visitor, the strange visitor, it is a strange visitor indeed, is a point source without any appearance of halo, comet, comma, or gas around it. The color is actually more consistent with the asteroid than the comets. And it has an unusually large brightness range, which means that they have tumbled, and with a access ratio at least 6:1, perhaps 9 or 10:1. And its size is of order 100 meters. It's tumbling at a period roughly of 8 hours, and it has a velocity that, if you extrapolate the velocity, what velocity it had when it came into the solar system, it was actually very, very slow. It was very close to the so-called local center of rest, which a phenomena which I'll describe a little later more in detail. And finally, one of the most puzzling issue is that it has a non-gravitational acceleration, as if though there's some other force is acting up on it. As they say in Star Wars, may the force be with you. And so putting all of these challenges together, it tells you that the amount of all these cometary interstellar objects may be huge. There may be a large population, as I said before, somewhere between 10 to the 13 to 10 to the 15 of these objects per cubic parsec. That means between here and the nearest, our nearest neighbors, there are, trillions of these objects, even comparable to our national budget in dollars. So when all of this all of these issues coming up with extreme elongated shape and this non-gravitational acceleration, it motivated some well-established public figure to suggest that it may be something like due to a alien spaceship. And this received a lot of publicity. Avi Loeb is a professor and a former chairman of the Department of Astronomy at Harvard. And he made his argument based on 5 easy pieces. He says the strange shape is probably more like a flat oblate shape antenna, kind of like an antenna dish outside Stanford, and that stands out and from the horizon, or a hamburger in space. That the non-gravitational acceleration, he argues, is a byproduct. It's not designed, but it's a byproduct if you put something like that out there with a very, very low density and extended antenna. And then when the solar radiation shines up on it, and it can actually give a little push. This is called the solar sail. And he argues that this may account for the use of solar sail idea. And then this rich population, he makes argument, you infer that rich population only because you think that these things are moving at random in the interstellar space. But if they all know that they want to come towards the Earth's direction, then you don't need to have such a large population. This is kind of trying to either catch salmon in the vast ocean, or you wait at the mouth of the stream because you know they all come. So if you see a few salmons at the mouth of the stream, you don't have to infer there's a huge population of salmon out there in the ocean. Then he argues that the tumbling motion, maybe even it was done by design. So because if you tumble, then the area of this dish can face all directions, so you can scan the entire sky instead of one direction. And then he argues that the fact that it's not moving very fast compared to the rest of the galaxy is because we're near a galactic parking lot. And he's never short of controversy and stimulation. He even wanted to link this with the very recently reported finding from the Office of National Intelligence on the so-called, unidentified area phenomena. It used to be called UFO. And here I quote what he said in Scientific America. He says, well, a predecessor of Oumuamua could have been a craft that deposited small probes into the Earth's atmosphere without being noticed because it was visited before Pan-STARR started its operation. Now, all of this is more likely to be argued by philosophers than scientists. And the difference between philosophers and scientists is that scientists need proofs. And as someone who I knew quite well before he died, had said in 1970.
Visited by a different extraterrestrial civilization every second Tuesday. But there's no support for this appealing idea. The extraordinary claims are not supported by extraordinary evidence.
There are curious daylight photos of UFOs. Some look suspiciously like hats or hubcaps thrown into the air. Photos can be faked. More common are unidentified lights at night. They're often aircraft, but if we can't identify a light, that doesn't make it a spaceship. Here's a movie of what you might think is a UFO. Actually, it's a piece of an asteroid burning up as it enters the Earth's atmosphere. Most reports of unidentified flying objects turn out to be something else, like a refracted image of a bright planet or the entry of an artificial satellite. Some are psychological aberrations, some are hoaxes. Never is there any compelling physical evidence, a detailed close-up photograph of a strange spacecraft, or a small device of extraterrestrial manufacture, or a book written in alien hieroglyphics. Never. There are reports of such things, but never the thing itself.
So it's well said, and in an attempt to follow the Sagan standard, and in fact, a Bay Area philanthropist and one of the co-founders of Google had sponsored a search for such an object through SETI, and to the best of my knowledge, that in fact, no radio signal has been detected in this frequency range. So if that's the case, is there a physical explanation for this? Well, I have to say it is very challenging to do it. And there are many hypotheses have been suggested, including when the star was formed and how they may be interacting with their neighbors, then their Kuiper Belt objects and asteroids got torn out of it and then thrown into space. But there are many challenges along the way to solve, to resolve all the 6 strange observational evidence. Well, let's have a look at close stellar encounter as one possibility. And we do know that many asteroids and comets actually come very close to the sun. Here plotted on the y-axis is the closest distance to the sun that you can get to. And this is the year of discovery. As you can see in recent years, we see many more because we have more sensitive instruments to detect them. And we see them come in near the sun. And here is one piece of comet that came close to the sun. And here is another that we think goes around massive black holes. A star may get torn apart. And we certainly know around Jupiter, Jupiter had encountered with perhaps a comet and that got torn apart. And one can ask the question that if such a phenomenon were to happen, is it possible this kind of phenomena could throw some of these pieces out in space? To do so, then my collaborator and I started to carry out a series of simulations. Here is a well-known type of approach using a computer simulation to send an asteroid close to another star. This star is not the sun, but it's around some other star, and that moved across that region. And when we look at this particular simulation, we can see that it moves around this host star at only a few times the radius of that star. So it gets a very, very strong pull. This is the direction of the sun. You can see it from the shadows. And here is the direction of the motion. It got pulled apart, kind of like, toffee candy and being pulled apart and by the gravity. And this pulling of the gravity actually can stretch things out. So the blue part are the ones that remains bound to the host star. The red part gets pushed to much larger distance and eventually escape the gravity of that original host star. So we can do this kind of simulation, and we can ask, what are the pieces that looks like? And could these pieces give you the kind of shape that you would like to see and give you the kind of spin rate? Here is the shape, and if it's one, that is like a sphere. If it is more like 0.2, it's more like a baguette and or hamburger. But most of the time, we find that they tend to produce baguettes than hamburgers. And then you can also look at the effective spin period from these type of simulation. So this is well-known physics and well-known study, and you can look at the shape, what it will produce, and you can ask, why is it 100 meters? And that 100 meters is how much you can survive due to the pole tearing of the gravity by these host stars as you get very close to them. And of course, it matters whether it's made of pile of sand or something that's have some material strengths, more like brick. And so you can play with all of these type of different material properties, and you can see under what condition they get torn apart, and you can do very systematic studies and look at the remnants and the shape and the spin rate and the tumbling motion. So these are reproducible, and you don't need a miracle. Okay, so now can we account for the appearance that is mostly look like a rock? So if they go very close to the star and they get heated up, but only for a short period of time, and the surface gets heated up, and the heat then will try to diffuse deeper into these asteroids, and but it takes time. In the meantime, this object is flying away from that original star and it's gradually losing the heat from the surface. This is kind of like making a steak, and if you want to have the inside being very moist, you turn up the heat to very high temperature first, and to brown the outside, and then the inside it remains relatively low temperature. It depends on how long you put it on the stove, and if you put it on a long time, the whole thing gets cooked. If you remove it shortly after, and you can have very pink meat inside and with brownish outside. And that is one way to get rid of all of the volatile material out and leaving behind relatively rocky material. Okay, and also this can change the material strengths. For example, here is an example, the outside, after it gets browned, and then it solidifies, and it can hold the inside better. And it can, as a result, you can actually produce even more elongated objects and even longer objects as a result. But using this method, we can actually try to decipher something about the original body. And this is kind of like a chocolate and with a solid coat outside and gooey caramel on the inside. So where was this, what kind of star could have hosted this object? It's probably more likely to be the low mass stars, because there are many more of those around in the solar neighborhood, and one can calculate their population and work out the kind of population that you expect. So what about the object that got torn apart, the asteroid? What could they be due to? They could have been formed around many stars, and we see around these young stars, they have dusty material, and old stars, we have see debris, like almost like a Kuiper belt type of objects, and they are very common. And during the formation of the solar system, and these objects can get scattered by the emergence of other planets, and as a result, they can get tossed to the neighborhood of their host star. And in fact, we see there's a discovery of another interstellar visitor. This time is called Borisov 2I. And this object was discovered by an amateur astronomer in Russia. And but it's completely different from Oumuamua in the sense that it's bigger and it's icier, and it has an orbit that looks like that it's been moving around the the interstellar medium for a while. It has much larger speed. So its trajectory is very different from that of Oumuamua. And so in fact, it's much easier to explain Morozov than Oumuamua. So the parent body from Oumuamua could very well be long period comets. And we see these comets come in to the neighborhood of the sun, and including things that is like Halley's Comet or even longer period systems. So this is, during these encounters with the original host star, you can have what is called tidal downsizing. You break up a large object, and you can make many into many smaller objects. So this is one way of making a factory of these debris and then toss them into the interstellar space. And it's kind of like picking up a corn and peel off all of the corn individual seed and then spread them all over the interstellar space. And because there are tidal downsizing, it's also possible that you can even send planets to the neighborhood of their host star, and then these planets would then get torn apart. We know these planets are very common around nearby stars, and a lot of that discovery were made here at NASA Ames using the Kepler space telescope to detect them. Okay, let me move, yes. The next I want to talk about is its motion relative to our neighboring stars. So there are ways to find our neighbors. One way is to see whether they're located at the same location. Another is to find our neighbors that have very similar speed as us. And so that's two different ways of finding who are your friends. And so if we look at their speed in the motion around the galaxy, and we see that there are many young stars which are moving together with very similar speed. And then there are older stars that move with a relatively larger speed. Okay, so this region where we see there's hardly very large relative speed, we call it the local standard of rest. You can look at the velocity of the stars as they age. They start to become more and more excited, and they move relative to the local standard of rest faster and faster. So the younger the star it is, the closer they're to the so-called local standard of rest. And Oumuamua, if you look at the orbit before it came into the solar system, was very close to the local center of rest. So you could say that maybe the parent body of this thing is very young. But if the parent body is very young, the host star is very young, then you have to have even more populations because they have to generate a lot more. So another way to do it is to say maybe Oumuamua is not quite like a standard star, but it has a finite size. It could be moving into this interstellar medium, and as it moves through the interstellar medium, it may feel a little bit of drag. So if I jump off an airplane, I don't speed up, all the way to 8 kilometers per second. In fact, I get to about 1,000th of that. But that's fast enough, and I will break every bone in my body. Nevertheless, and there's a terminal speed, and that is due to the air resistance. And maybe this could account for it. And but this is also very, very interesting is when you try to account for that, and you find that they are indeed in the solar neighborhood. They are young star clusters, and these young star clusters and recently have been identified. Maybe even 50 million years ago, it came from this region. And as you can see in here, there's a lot of clouds. And these clouds are very turbulent. They move all over the place. So if Oumuamua is actually moving through this, it's a little bit like for those who like to play golf or those who like to watch soccer, and you see this really good soccer player, and when he kicked the ball, you see the curvature of that ball. Okay, this is a curve through a curveball for those who are baseball enthusiasts, and for those who play golf, you know you have a slider. And what is that slider due to is a force called Magnus force. And that can actually randomize your motion by a lot. And so if it's a spacecraft, you have, even if you aim it at the Earth extremely sharply, and its orbit will, its direction will change. And that would really make it completely different. So that association is probably not necessarily satisfied. So there's another effect, which is like the interstellar medium is also contains a lot of magnetic fields, and these magnetic fields, when you have an object move through the magnetic field, and they feel some resistance. In fact, the first generation of NASA satellites that was sent up in the 60s, and they keep on coming down very quickly, and these satellites are thought to be brought down partially by this so-called unipolar induction or Elfin wing reaction to the Earth's magnetic field. And so this kind of phenomena could happen in the interstellar medium, and that would make these objects close to the center of rest. And if you look at this effect, it does depend on the size. Something like Borisov is larger, and they will have larger, they have more inertia, so they don't get slowed down as much. Okay, so and then this acceleration. So one way to get this non-gravitational acceleration is so-called outgassing. If you shine light on it, there is gas that comes out, and maybe this gives a push. And some people made the first estimate suggest that there's not enough energy received by Oumuamua and to get accelerated this way. So there were some very innovative ideas. Maybe hydrogen molecules gets deposited on the surface of these objects, and then when they come by and they evaporate, and then they can get moved out. There are even suggestions that the whole place is covered with a nitrogen ice, like what you see on Pluto, and maybe that's one way to do it. But we don't see carbon monoxide around Oumuamua, and so yet, around all comets, when you see a halo, they're usually dominated by CO. So you look at what else is available, and it seems that water is still possible. So let's revisit the water outgassing. And since that we use this type of elongated shape, and is it possible that you evaporate most of the surface area, you get rid of the CO, and then you only leave behind some water down deep in the interior, and then they can leak out in this manner. This is kind of like a very soft boiled egg. The inside can still be preserved as a liquid, and outside is solidified. And one way to do that is to get this kind of outgassing, and that turns out is possible to do. I'm running through the last couple of slides, few slides, so I can finish on time for you to have some questions. And so if you use this kind of outgassing, then you can actually jet these things through. But these type of consideration can also provide arguments, constraints on the spaceship hypothesis. So what do we look forward to? There is a large telescope called the Vera Rubin telescope, used to be called the LSST, and that's built in Chile, that's being built currently, and that will be 100 times more sensitive than the very telescope on Hawaii that we use to find Oumuamua. So we probably will find a lot of them. And they may be produced in this manner. So in summary, I like just to say the asteroidal interstellar objects tends to be smaller and more common than the cometary. The cometary is the one that Borisov found. And these asteroidal interstellar objects may have small speeds relative to local standard rest, not because they're young, but because they feel the resistance of either by magnetic field or by the gas. And they can be reproduced. All of their attributes can be reproduced physically. There are some uncertainties, and but it's easier to swallow those uncertainties than to invoke a very innovative, very creative sort of alien idea. And because if if these objects can fly from stars to another star, it tells you it's possible that they may even carry some substance from one location to another, not necessarily by intent, but perhaps it provides a possibility of proliferation, a bit like the pandemic virus, and that can spread out. And so this idea of panspermia is possible, though we don't know what the likelihood that is for it to carry life. So on that note, I just want to show you this picture to show you that all of these efforts to detect life elsewhere in the universe gets a boost from this type of analysis. Thank you very much.
Thank you, Professor Lin. We've got quite a few questions in the chat here. I just want to remind folks that if you'd like to ask the question yourself, please raise your hand and we'll do our best to get to you and allow you to, hope you'll unmute yourself and pose the question audibly and visibly yourself. All right, I won't necessarily go in order here, but I want to ask the first question. Please forgive me, audience here. I asked in the chat here, did anyone detect Oumuamua on its way in, Professor Lin? No. Perhaps even retroactively, went back to the data and looked for it?
Well, retroactively, there were some attempts to do it, and but they didn't see it. And I think that's very unfortunate, because you would have thought, it's been switched on for a few months by then, and you should have been able to pick up some signal, but it was not. And so they saw it already after peri-astro.
Do you think the issue was that it was just simply bad luck that it was unobserved, or that it was in a bad position, bad order?
Yeah, well, the telescope is, gradually, it's like a new car, you get tuned up. And so it's still in the tuning process. And so it's the first few months of operation. So then they eventually found it. Now, if it had been there for many years, then that would be a surprise. That would be something we should really ask this question. Why is it that you haven't seen it?
Yes, thank you. Dave asks, if the 30-meter telescope were working, would it have been able to detect a decent picture of Oumuamua? If not, how big a telescope would be needed?
I think, I'm not 100% sure. I think there was an attempt to take image, certainly with a VLT and in Chile, and I think also probably Czech, but I'm not certain. And the important thing here is that you got to respond to the alert very, very quickly, because it's moving away from the solar system. And you're racing with time, basically. And so I think with some objects like this size, to resolve an object with a 30-meter telescope you probably could do it, when it's within the orbit of, while it's within the orbit of asteroid region. We should be able, down to this size, it would still be resolvable. And I mean, you're talking about 100 meters. 100 meters is the Trans-America building, okay, or the Golden Gate Bridge. Okay, so you're trying to see it from the Earth in Golden Gate Bridge, and you need to have a resolving power. That's what it is.
Got it. Thank you. Marilyn asks, why, in reference to one or two of your slides, why do older stars move faster?
Okay. So when stars are born, they're born in clouds, and the clouds, they run into each other. So they can never move too fast, because if they move too fast, they run into each other and they settle down. But once they form a star, they don't see each other anymore. So they agitate each other. There's no damper. And so if you accumulate over time, the longer you wait, the more they excite each other, they perturb each other, okay? There's more and more damper, okay? So it's kind of like a family, and there's quarrels between siblings. And when they're very, very young, there's, a damper. Their parents are damping, so they never get too eccentric. But when they get very old, the damper is gone. And then they get very agitated. That's equivalent. That's the analogy you can make in terms of the motion of the stars.
Got it. Marilyn, I hope you like that. Dave asks, why doesn't the local standard of rest have U equals 0 and V equals 0 on the graph you showed? And what exactly do U and V mean?
Yes. So there are three directions. Okay, there is there's a galactic plane. One is going up, and one is going to the side, and one is going out. So you can have a disk, and one is sideways, one is outward, one is up. Okay, so these are the U, V, W, or whatever. And then the group, when you form a star, they don't have to be in a very circular orbit. Okay, they can be. This group can have a little motion relative to all this. So the center of that, it's not important when you see a group of people on a Caltrain that's moving, that there's a systematic motion. But what is relevant is in the compartment of the Caltrain, whether they are running away from each other very fast or they stay relatively close. But the motion, the platform they set out is still moving.
Good. Thank you, Professor Lin. I see that Michael Bolte has written a rather lengthy answer to the earlier question regarding the ability to observe to observe Oumuamua. I'll leave that to our audience to read if they'd like. John Gullickson asks, for the less scientific people in the audience, like me, he says, on a scale of 1 to 10, how freaked out are you, Douglas, by this object? Why did you choose the number you chose? I'm not sure what he's referring to there. Also, for non-scientists, on a scale from 1 to 10, how freaked out should we be? Thank you for this very interesting presentation.
Okay, so the reason I'm attracted to science is because I like to solve puzzles. In fact, I'm not freaked out, but I'm more really excited by these clues, and it gives me an opportunity to try to solve it in a way that's a little bit like a detective story. And each time I look up and I find a little extra evidence here and there. And you had originally many ideas on how the scene was, the crime was performed, but you have to correct yourself all the way along because you discover something else that doesn't quite fit in your original idea. So this has been very exciting for me. I didn't jump into this right from the beginning, but as I heard various talks, people talk about more and more crazy ideas. I said, oh, maybe I can look at it from a different perspective. So that's why I was very interested. And I think the expression freaked out means that you're terrified. And terrified, if it's something that is not known, if you don't know your fate, you should be terrified. But if we can figure out what is really going on, maybe it's not so frightening. And maybe it's just a fun, just like these UFOs, and it's probably more like a local phenomena than some aliens trying to invade us, and it doesn't make sense. And if you were to have something that was coming in to plan all these probes around the Earth, then when the real mission comes, why doesn't it channel itself to stay in the solar system? Why does it just come and then leave right away? And so it just doesn't make that kind of sense. So I think before one gets freaked out and do an overreaction onto things that is perhaps not so rational, and it's better to analyze what is maybe the cause, underlying cause, and then to do series of tests on that. That's the exciting thing. It's what is the next step? By Carl Sagan's standard, how do we actually provide evidence? And he asked me a very good question. But the numbers you put in, how do you know these are the right numbers? Okay. Initially, we don't. So we put in some numbers and we test it, and these numbers have implications. It implies observations that can be done to check them. And science is not about an absolute fact. It is about a method. It's a methodology that enables you gradually coming closer and closer to understanding the event and to sort out many different exciting ideas, as Carl Sagan would say. So that's my answer.
So the famous quote, I guess Sagan's, and maybe going back to David Hume, that extraordinary claims require extraordinary evidence. Here, the evidence is not extraordinary enough to assign this alien artificial creation.
Not yet.
Yes, yeah. Thank you for the question. I have one final question here from Jim Lilienthal. Can you comment on the question of projecting a very high frequency of interstellar objects from this passage, even though it was shortly after the activation of the Haleakala telescope, given that we still have only an N of 1 for this particular kind of object?
Excellent question. So we don't have to wait very long to verify that, because with a Vera Rubin telescope, it's going to be 100 times more sensitive. We're going to see these events once every week, okay? And then you can no longer need to, the first thing is that you see, when you see, let's say when you see one salmon in the ocean, you say, oh, there's salmon in the ocean. I've only been here for an hour. There must be tons of salmon in here. But if you stay here and you improve your catching, ability, and then you can actually work out. You can figure out how many salmons there are because you have ability to improve your detection method. If we don't ever see one again, then I say that's incredible coincidence. But let's build on that first and see what we can do. And if that is the case, and then we try to infer, make predictions that can be checked.
Great. I end tonight by offering 3 big thank yous. First, to you, our Zoom audience. It's great to gather, even if just online, with like-minded, curious folks. Thank you for being here. And thank you to those of you who financially support the Mount Tamalpais Astronomy Program and Wonderfest. But most of all, our third thank you to our speaker, Dr. Doug Lin. Thanks very much. How about a American Sign Language silent round of applause, visible applause, or the good old reaction of clapping hands? Thank you, Doug.
Thank you.
Thanks so much.
Thank you.
Good night, all.
Good night. Thank you.
So I'll open my arms and eyes and wonder every day till the day I die. No one really knows why gravity exists. Naming something doesn't mean that we get it. So I'll live each day